So we are given this recurrence for t of n, and we want to prove formally that t of n is in big omega of n log n. We want to prove formally that our guess from the last video, based on the recursion tree method, that n log n is going to be a lower bound on t of n, is a valid guess, and we want to prove that formally. More specifically, from the definition of the big omega notation, we want to prove that there exists a positive constant c and a positive threshold n0, such that for all values of n larger than or equal to this threshold n0, that is, for all sufficiently large values of n, t of n can be bounded from below by a constant multiple of n log n. This is the overall claim that we want to prove. So let's look at the base cases. Let's start from the smallest possible value of n, which is n equal to 0. Is t of 0 greater than or equal to c times 0 times log of 0? Well, log of 0 is not defined. So the right hand side of this inequality is not defined. It's undefined. So this inequality therefore doesn't hold at n equal to 0. So our base case for n equal to 0 fails. So n equal to 0 is not really a base case, because this inequality doesn't apply at n equal to 0. But this doesn't mean that our overall claim is false, because our claim assumes that it's true beyond a certain threshold n0. So because this inequality failed at n equal to 0, it means that this threshold cannot be equal to 0. It will need to be some value greater than 0. It will be the first value that we find for which the inequality will actually hold. So let's try n equal to 1. Is t of 1 greater than or equal to c times 1 times log of 1? Well, t of 1 is equal to 1, and c times 1 times log of 1 is 0, because log of 1 is 0. So the left hand side is 1, the right hand side is 0, and so this inequality does hold at n equal to 1. So this is a valid base case. We have proven that at n equal to 1 the claim is valid. What about n equal to 2? Is t of 2 greater than or equal to c times 2 times log of 2? We can calculate what t of 2 is by using this recurrence. I won't do that here because the exact value of t of 2 doesn't matter as long as we know that it's going to be some positive number, some positive constant. This inequality will hold at t equal to 2, provided that c is less than or equal to t of 2 divided by 2 log 2. So if we choose a value of c that's positive, of course, but less than this constant, whatever this constant is. So if we choose a value of c in this range, then the claim will be true for n equal to 2. Similarly, we can prove that the claim will be true at n equal to 3, provided that c is less than or equal to t of 3 divided by 3 log 3. T of 3 is going to be some constant which we can evaluate using this recurrence. And so the right hand side here is going to be a constant. And if we choose a value of c that's less than or equal to this constant, then this claim will hold for n equal to 3. Now if we choose a value of c that's less than or equal to both these constants, then the claim will hold, this claim will hold for both n equal to 2 and n equal to 3. So in this way, we can go up to any constant b. If we want to prove the first, if you want to prove that this claim is true for the first 15 numbers, we can prove that in the same way. We'll get 50 inequalities that we need to satisfy for C, 50 constraints for C, and if we choose a value of C less than or equal to all of those 50 constants on the right hand side, then we can say that this claim will hold for all those 50 numbers. So let's not worry about how many base cases we exactly need to prove. As long as it's some constant number, as long as the base cases vary from 1 up to some constant b, we can easily prove that every single base case from 1 onwards is going to be true, provided the value of c is chosen to be less than or equal to the minimum of all these values. So let's then move on to the induction hypothesis. Having proven the base case, let's assume that the general claim, which is this claim, is true for all values of k up to n minus 1, starting from 1, which was our first base case. So assume that for all values of k from 1 to n minus 1, the claim is true. That is, for all those values of k, t of k is bounded from below by ck log k. T of k is greater than or equal to ck log k for some constant that's positive. So we are using strong induction again. We are assuming that the claim holds for all numbers up to n minus 1, and we are going to prove that assuming this, we can prove that the claim also holds at n. That is, we need to prove that t of n is greater than or equal to cn log n. So let's use the induction hypothesis to prove this induction step. We are given that t of n is t of n by 3 plus t of 2n by 3 plus n in the recurrence. This is basically the definition of the recurrence itself. Now because n by 3 and 2n by 3, with their floor operators of course, are going to be less than n, we can assume that the induction hypothesis can be applied for these values of the subproblem. That is, we can assume that t of n by 3 is greater than or equal to c times n by 3 times log of n by 3, and t of 2n by 3 is greater than or equal to c times 2n by 3 times log of 2n by 3. So we are saying that for k equal to the floor of n by 3 and k equal to the floor of 2n by 3, the induction hypothesis is true, because these numbers are going to be less than n. And of course they also need to be greater than or equal to 1. This means that the value of n needs to be at least 3 so that the floor of n by 3 and the floor of 2n by 3, both of them fall into this range. And for lower values of n, for values of n lower than 3, we can assume that we have proven that the claim holds for those values as part of the base cases and the set of base cases itself. So we can use the induction hypothesis and substitute the right hand side of these inequalities for these terms. By doing so, we would be increasing the value of the right hand side because both these terms are being replaced by their lower bounds. So we'll be decreasing the value of the right hand side because both these terms are being replaced by their lower bounds. So as a result of this substitution, the resulting expression will have a lower value than what it had before. So c times n by 3 times log of n by 3 plus c times 2n by 3 times log of 2n by 3 plus n is less than or equal to the original expression. So t of n is greater than or equal to the resulting expression. Now this is a little complicated expression. We need to simplify it because ultimately what do we want to prove? We want to prove that t of n is greater than or equal to Cn log n. So if we are able to show that this expression is greater than or equal to Cn log n, then we would have proven that t of n is greater than or equal to Cn log n, because by transitivity, if t of n is greater than or equal to this, and if this is greater than or equal to Cn log n, then by simple transitivity, t of n can be claimed to be greater than or equal to Cn log n. But to prove that this is greater than or equal to Cn log n, we need to do some simplification because there are these floor operators inside this expression. So let's try to simplify it. Let's replace these floor operators by the number n by 3. So let's replace the floor of n, the floor of n, all these numbers here, by the number minus 1. And why can we do that? Because the floor of n is greater than n minus 1. The floor of 2.5, for example, is greater than 2.5 minus 1. What is the floor of 2.5? It's 2. 2 is greater than 1.5. So this is of course trivially true if n is an integer itself, because n will be greater than n minus 1. But even if n is a fraction above some integer, by subtracting 1 from n, you will fall below the floor of n. And so this is true. Now because this is true, when we replace the floor of n by 3, for example, by n by 3 minus 1, or when we replace the floor of 2n by 3 here by 2n by 3 minus 1, we are further decreasing the value of this expression because we are replacing these terms by something smaller than them in general. So, or at most something equal to them. So we can say that this expression will be greater than or equal to c times n by 3 minus 1 times log of n by 3 minus 1 plus c times 2n by 3 minus 1 times log of 2n by 3 minus 1 plus n. So we have uniformly replaced the floor of n by n minus 1 everywhere. Now this expression is still a little complicated because now we have log of something minus 1 here. It's not clear how we're going to deal with this expression. So let's try to further simplify it. Again, we have to keep in mind that we want to prove that this needs to be greater than or equal to Cn log n. But right now there is no way to get log n in this expression, even though we could get Cn by multiplying C times n here. But then it's going to be combined with log of n by 3 minus 1. So how do we make this log n? If we could make this log n, if we could make this log of 2n or 2n by 3 or n by 3 here, basically if we could remove these minus 1s, then we could simplify things a little. So how do we do that? For further simplification, let's note that log of a number x minus 1 will be greater than log of x minus 1, the minus 1 outside. The log of x minus 1 is nothing but log of x minus, this 1 can be written as log of 2 to the base 2. And log of x minus log of 2 is log of x divided by 2. So in general, log of x minus 1 will be greater than log of x by 2 whenever the argument of the log x minus 1 is greater than x by 2, because log is a monotonically increasing function of the argument. So if one argument is larger than the other argument, log of that argument will also be larger than log of the other argument. So when is x minus 1 greater than x by 2? Well, we can bring x by 2 on the left hand side. We'll get x minus x by 2 is greater than 1. That is, x by 2 needs to be greater than 1, or x needs to be greater than 2. So as long as the argument here is greater than 2, log of that argument minus 1 is greater than log of that argument with the minus 1 outside. So we can use this to pull this minus 1 outside the log and thereby have a log of n term which can be combined with Cn. So we are going to replace log of n by 3 minus 1 by log of n by 3 minus 1. So this is what we'll get. We start from this inequality and you substitute log of n by 3 minus 1 outside. We'll get this term. Similarly, if we take log of 2n by 3 minus 1 and substitute it with log of 2n by 3 minus 1, we are basically replacing both these terms by something smaller. Right? These two terms have been replaced by something smaller than them. Now, this is obviously going to be true if n by 3 is greater than 2 and if 2n by 3 is greater than 2, because this inequality applies for values of this x greater than 2. So again, that translates to n needing to be greater than 6, because if n by 3 needs to be greater than 2 and if 2n by 3 needs to be greater than 2, both these conditions will be true if n is greater than 6. So what we'll assume is for values of n less than 6, less than or equal to 6, let's prove that the claim is true for those values of n within the base case itself. So, since we are replacing these values by something smaller now, we can say that we have further reduced the value of this expression into this expression. Now, log of n by 3 minus 1 is nothing but log of n by 3 minus log of, this is log of n by 3 minus log of 2 because log of 2 is 1. This in turn can be written as log of n minus log of 3 minus log of 2. We can combine log of 3 and log of 2 here to get log of 6. So this will be log of n minus log of 6. Similarly, let's simplify this a little bit by opening it up. We'll get log of 2 plus log of n minus log of 3 minus 1, which is again log of 2. So the log of 2 and the log of 2 here with a negative sign will cancel each other out, and we'll get log of n minus log of 3 here. The other terms are the same. Now let's open up these brackets completely. So we'll have 4 terms here by opening up these two expressions and multiplying them term by term. And we'll get 4 more terms here. So we'll have a total of 9 terms when we open up these brackets. 1, 2, 3, 4, 5, 6, 7, 8, 9. If I take the first term here and multiply it with the first term here, I'll get Cn by 3 times log n. If I take the first term here and I multiply it with the second term here, I'll get minus Cn by 3 log 6. If I take the second term here and multiply it with the first term here, I'll get minus C log n. If I take the second term here and I multiply it with the second term here, I'll get minus C times minus log 6, which is plus C log 6. So these are the first 4 terms. The next 4 terms will be obtained by multiplying these 2 terms with these 2 terms, again term by term. So if I multiply the first term here, which is 2cn by 3 with log n, I'll get 2cn by 3 times log n. If I take the first term here and I multiply it with the second term here, I'll get minus 2cn by 3 log 3. If I take the second term here, which is minus c, and I multiply it with log n, I'll get minus c log n. If I take the second term here, minus c, and I multiply it with minus log 3, I'll get plus c log 3. So these are the 4 terms that will be formed by opening up these brackets and multiplying term by term. And then we'll have this plus n by itself at the end. Now we can group these terms based on what the powers of n are, or what the growth rate of each term with respect to n is. These 2 terms which I have underlined in red here have an n log n, are of the form some constant times n log n. So let's group together these 2 n log n terms and let's add together their constant coefficients. So what will be the result? N log n multiplied by c by 3 plus 2c by 3. C by 3 plus 2c by 3 is 3c by 3, which is simply c. So we'll get c times n log n in the result. Let's group together the log n terms, and I've underlined the 2 log n terms here with green, and if we combine them we'll get minus 2c log n. I've also grouped together the n terms where the term has an n in it, just an n by itself with a constant coefficient. So there are 3 such yellow terms. And if we group these yellow terms together and take n common, from the first term we'll get a 1. From this term we'll get a minus c by 3 times log 6 inside the brackets. And from this third term we'll get minus 2c by 3 times log 3 inside the brackets. And finally these 2 pink terms are constants by themselves without any power of n or log n term inside. They are pure constants. So we can group them together, and if we take c common, we'll get log of 6 plus log of 3, which is log of 18. 6 times 3. So what we get is t of n is greater than or equal to this expression. Now we want to prove that t of n is greater than or equal to Cn log n. Now we have a Cn log n term as a result of opening up all these terms. Now we get a Cn log n over here. And all the simplifications we did, whether it's deleting these floor operators and replacing them by the number -1, or taking these log of something -1 terms and pulling out the -1 outside. All those were ultimately meant to enable us to combine c times n with log n so that we get what we need to prove on the right hand side. But then we also got these extra terms. For t of n to be greater than or equal to just this first term by itself, the remaining terms should add up to something positive. Right? Because if t of n is greater than or equal to Cn log n plus something positive, then we can say that t of n is definitely greater than or equal to Cn log n. Because if it's greater than or equal to the sum of these two positive expressions, then it's definitely greater than or equal to this first expression by itself. So if these non-red terms add up to something greater than 0, then we can claim that t of n, or this whole expression will be greater than or equal to Cn log n. Or we could directly say that we want this expression to be greater than or equal to Cn log n, and see what needs to happen for that to be true. So if we say that this needs to be greater than or equal to Cn log n will cancel out on both sides, and we'll get the remaining terms need to be greater than 0. It's the same. So what are these three terms? This first term is a log n term with some coefficient. Second term is an n term with some coefficient. And the third term is some constant. So we can think of these terms in the following way. The dominant term is this n term, because this term is a constant and this term is basically a log n term. So this is the dominant term. N times some constant coefficient minus log n times some other constant coefficient plus some other constant coefficient. This needs to be greater than 0 for this whole expression to be greater than 0. So being the dominant term, we know that as n becomes large enough, assuming that whatever the coefficients, sum of all the coefficients here are greater than 0. So these round brackets contain the actual coefficients, which I haven't shown explicitly here, because I want to emphasize here that if this coefficient is positive, then as n becomes large enough, it will definitely be true that this term will dominate the values of these other two terms. These other two terms will become insignificant relative to the value of the dominant term for some large enough n. We are guaranteed of that, provided that this constant coefficient of the dominant term is greater than 0. So let's enforce that the coefficient of n should be greater than 0. This means that this needs to be greater than 0. 1 minus c by 3 times log 6 minus 2c by 3 times log 3. This needs to be greater than 0. And when will this be greater than 0? We can take the c terms on the other side and take c common. We'll get 1 by 3 log 6 plus 2 by 3 log 3. And this needs to be less than 1. Basically, we are taking these two terms on the other side, so the sign will become positive, and the sum of those two terms needs to be less than 1. And those two terms can be written as c times 1 by 3 log 6 plus 2 by 3 log 3. This needs to be less than 1, which means c needs to be less than this positive constant. Note that this is a positive number because the denominator is positive and it's some constant. Let's not worry about what the exact value of this constant is. But as long as the value of c is chosen to be less than this constant. So let's say on the number line this constant maps to some point over here. If we choose a value of c in this range, we are guaranteed that the coefficient of n will be positive. And if the coefficient of n is positive, then we are guaranteed that this whole expression will be greater than 0 for large enough n. And if that is true, then we are guaranteed that Cn log n plus this expression is going to be greater than or equal to Cn log n. And if that is true, then we are guaranteed that T of n is greater than or equal to Cn log n. And if that is true, then we are guaranteed that T of n is greater than or equal to Cn log n for all values of n greater than or equal to 1. Because we've already proven that this claim is true for all the base cases. And now we've proven that if C can satisfy this additional constraint, from the base cases we got a set of constraints for C. And from the inductive step we are getting one additional constraint for C. So if C can be chosen to be less than the right hand side of all those constraints. So note that all the constraints were of this form. C needs to be less than some constant k1, C needs to be less than some constant k2, and so on. There are a bunch of constraints like this. A constant number of constraints, of course. The last of which comes from the inductive step, and the remaining come from the base cases. So if we choose a value of C that's less than the minimum of the right hand side of all those constraints, we are guaranteed that the claim holds, this claim which we want to prove will hold for all base cases and will hold for all n greater than or equal to 1, because 1 was the first base case for which the claim was true. So if we choose a value of C less than right hand side of all the constraints we had for C, then we can say that T of n will be bounded from below by C times n log n for all n greater than or equal to 1. This means that T of n will be in big omega of n log n, because there does exist a positive constant C for which T of n is bounded from below by C times n log n for all n greater than or equal to 1. And this is the definition of the big omega notation. So to summarize, we have proven that this recurrence has the solution T of n is big omega of n log n, and in the previous couple of videos we showed that this recurrence also has, so T of n is also in big O of n log n. That's what we proved in the last few videos. And in this video we proved formally using the substitution method that our guess about the lower bound on T of n, which was this n log n bound, was also a correct guess, because we have formally proven that T of n is in big omega of n log n. Now since T of n is in both big O and big omega of n log n, we can conclude that for this recurrence, the solution to this recurrence is T of n is theta of n log n. This is, n log n is a tight bound on T of n. It's not just a lower bound, and it's not just an upper bound. It's both a lower bound and an upper bound, which means it's a tight bound on T of n. So T of n is in theta of n log n. And we proved this using the substitution method. We took the help of the recursion tree method just to help us in generating good guesses. But it was not very easy to formally prove this solution from the recursion tree method itself, because the form or the shape of the tree was pretty irregular. So we relied on the substitution method here to prove this claim. And note that in the process of trying to prove this claim, we also ended up computing valid ranges for the values of C. So we ended up narrowing down a particular range for the values of C, and we also ended up computing what n naught should be in the process of trying to prove this. We are trying to prove that there exists these two positive constants, and we also obtained values or a range of possible valid values for these constants from the proof itself. So the substitution method helps us not only in proving this claim in general, it also helps us in narrowing down what these constants could be. And we can pick any value from the valid range that we got for C.